Now I am taking the topic non-aqueous solvent. First is the properties of solvents. Now what is a solvent? A solvent is defined as a substance which has the power of dissolving other substances. Water is an excellent solvent. There are three types of liquid substances, that is molecular liquids, ionic liquids and atomic liquids. Both of them can serve as solvents. They dissolve solutes that are solid, liquid or gaseous and then form solutions. First is the molecular liquids. Molecular liquids include water, many organic solvents and some inorganic solvents such as hydrogen fluoride, liquid ammonia and sulfur dioxide. Ionic liquids are mostly molten salts and usually used at relatively high temperatures. Ionic liquids are used as a kind of green solvents. Metallic mercury is used as an atomic liquid solvent. Besides these liquid solvents, superficial fluids are sometimes used as media for chemical reactions and separations. Molecular solvents other than water are generally called non-aqueous solvents. That is, a non-aqueous solvent is a molecular solvent. Water. At first, we are considering the case of molecular solvent, water. Water is a universal solvent. Then what are the properties of water? It has high dielectric constant, long liquid range, liquid at ordinary temperature and it is highly available. Next, non-aqueous solvents. Non-aqueous solvent is a molecular solvent other than water. Non-aqueous solvents are water-free fluids that dissolve certain salts in the same way as water. Common examples of non-aqueous solvents are liquid ammonia, liquid sulfur dioxide, hydrogen fluoride, dinitrogen tetroxide and phosphorus oxychloride. Next is autoionization theory of solvent. On autoionization, a solvent splits into two parts, that is, acidic part and a basic part. Substances that increases the concentration of acidic part behaves as an acid and substances that increases the concentration of basic part behaves as a base. Ammonium chloride undergoes autoionization in the presence of solvent ammonia, that is NH4++ and Cl-. Cl- act as an acid. Sodamide undergoes autoionization in presence of solvent ammonia to form Na++ and NH2-. In this case, NH2- act as a base. FeCl3 undergoes autoionization in presence of solvent POCl3 to form POCl2 plus FeCl4-. In this case, FeCl4- act as an acid. Superacids. Superacids are extremely strong acids, that is much stronger than mineral acids such as sulfuric acid and hydrochloric acid. Acidity means the ability to add protons. That is, stronger the acid, the greater is its power to protonate other substances. A superacid is defined as a substance that has a higher H+ chemical potential than 100% pure sulfuric acid. Superacids are extremely stronger than conventional strong mineral bronzed acids such as sulfuric acid or Lewis acids like aluminum chloride. J.B. Conant in 1927 gave the name superacids to acids that were capable of protonating certain weak bases such as carbonyl compounds. Pearson's HSAB principles. First is hard acids, soft acids and bases. Acids are mainly of two types, that is hard acids and soft acids. Bases are also of two types, hard bases and soft bases. Classification of metal ions and ligands. Alkali metal ions, alkaline earth metals and lighter transition metal ions in higher oxidation states are hard acids. That is, they belong to class A metal ion. Examples are Na+, Mg2+, Ba2+, Ka+, etc. Heavier transition metal ions in lower oxidation stage are called soft acids. They belong to class B metal ions. CO2+, Hg+, Ag+, Pd2+, Pt2+, etc. are soft acids. The ligands that bind preferably to class A metal ions are hard bases. That is OH-, F-, NH3, H2, etc. are hard bases. The ligands that bind preferably to class B metal ions are soft bases. Examples are PR3, R2S, ASR3, ASR3, SCN-, CO, etc. Pearson's principle. Consider the example BH plus CS3 Hg plus gives BCS3 Hg plus H plus. In this case, H plus is a hard acid, Hg plus is a soft acid, whereas B is the base. If B acts as a hard base, then it will have preference for a hard acid. So, equilibrium moves from right side to the left side. If B is a soft base, then it will have a preference for Hg plus, and in this case the equilibrium moves from left side to the right side. That is, Pearson principle states that hard acids will have a preference for hard bases and soft acids will have a preference for soft bases. Liquid ammonia. Liquid ammonia is a good solvent for organic molecules like esters, amines, benzenes, alcohols, etc. It is a better solvent for organic compounds than water, but it is a worse solvent for inorganic compounds. The solubility of inorganic salts is highly dependent on the identity of the counter ion. Due to less extensive hydrogen bonding, liquid ammonia is a better solvent for organic compounds which are more soluble than in water. Liquid ammonia shows a striking resemblance with the water in its solvent action. Ammonia molecules are less strongly associated through hydrogen bonding in liquid ammonia. Consequently, the freezing as well as boiling points of liquid ammonia are lower than those of water. Another similarity with the water is the polarity of liquid ammonia. It has a pyramidal structure which makes it polar. Another similarity is autoionization in liquid ammonia, similar to autoionization of water. They are represented as H2O gives H++ OH-. H plus again combines with one molecule of water to form hydronium ion H3O plus. That is 2H2O gives H3O plus plus OH minus. Two molecules of water combines together forming hydronium ion and hydroxyl ion. Kw is equal to concentration of H3O plus into concentration of OH minus. The value of this is 1 into 10 raised to minus 14 at 25 degree centigrade. NH3 dissociates as H plus plus NH2 minus. H plus combines with another ammonia molecule to form ammonium ion, that is NH4 plus. Two NH3 molecules dissociate forming NH4 plus plus NH2 minus. That is, it forms ammonium ion and amide ion. Chemical reactions in liquid ammonia. Liquid ammonia has water-like properties, and hence the reactions which take place in aqueous solutions can also occur in liquid ammonia solutions. First is precipitation reactions. Precipitation reactions normally involve double decomposition. The solubilities of various substances in liquid ammonia and water are different, and hence many reactions which are not normally possible in water have been reported to occur in liquid ammonia. Some of these reactions are: first is, consider the precipitation of silver chloride in aqueous medium. That is, KCl react with silver nitrate to form AgCl and KNO3. In liquid ammonia, the direction of the reaction is reversed. That is, AgCl react with KNO3 in the presence of liquid ammonia to form KCl and AgNO3. Similarly, a white precipitate of barium chloride is produced when the solutions of silver chloride and barium nitrate in liquid ammonia are brought together. Iodides and bromides get precipitated when solutions of various metal nitrates and ammonium halides in liquid ammonia are mixed together. That is, one of the reaction is SrNO3 twice strontium nitrate react with ammonium bromide in the presence of liquid ammonia to form strontium bromide and ammonium nitrate. Ammonium sulfide in liquid ammonia is capable of precipitating many metal sulfides from the solution of nitrates of metals. One of the example is NH4 twice S plus 2AgNO3 in presence of liquid ammonia forms Ag2S plus 2 molecules of NH4NO3. In many cases, soluble halides are precipitated as complex amines. Example is 2NaCl react with calcium nitrate and ammonia to form CaNH3 4 times Cl2 plus 2NaNO3. Acid-base reactions in liquid ammonia. There is a comparison between neutralization reaction in aqueous solution and in liquid ammonia solution. Hydrochloric acid gas dissolves in liquid ammonia, giving NH4 plus ions and Cl minus ions. A similar reaction also takes place in the case of water. That is, HCl plus H2O gives H3O plus plus Cl minus. In aqueous solution, the process of neutralization of a strong acid and a strong base involves the combination of H3O plus and OH minus ions to form unionized water. The anion of the acid and the cation of the base remaining unchanged. Consider the neutralization of hydrochloric acid with potassium hydroxide. That is HCl plus H2O gives H3O plus plus Cl minus. KOH gives OH minus plus K plus. That is H3O plus combines with OH minus to form two molecules of water. That is a case of neutralization. Consider the neutralization of ammonium chloride with the potassium amide. That is, ammonium chloride forms NH4 plus Cl minus. Potassium amide dissociates as NH2 minus plus K plus. The neutralization involves combination of NH4 plus NH2 minus ions to form unionized ammonia molecules that represent a case of neutralization. Reactions of amino acids. Amino acid is a substance which in liquid ammonia furnishes NH4 plus ion. The following reactions show their behavior to be similar to that of aqueous acids. First is the replacement of protons by reactive metals. Acids give out hydrogen with metals in aqueous solution. Likewise, the solutions of ammonium salts in liquid ammonia react with alkali and other metals to give hydrogen. Example, sodium metal react with ammonium ion in liquid ammonia to liberate hydrogen. CO react with ammonium nitrate in liquid ammonia to liberate hydrogen. Proteolysis. Certain compounds like urea, acetamide, etc., which are incapable of donating protons to water, can readily undergo proteolysis in liquid ammonia. That is, they can donate protons to ammonia in liquid ammonia. Hence, organic amides act as acids in liquid ammonia. Examples are NH2CONH2 plus NH3 gives NH minus CONH2 plus NH4 plus. CS3CONH2 plus NH3 gives CS3CONH minus plus NH4 plus. Similarly, sulfamic acid behaves as a dibasic acid in liquid ammonia. NH2SO2OH plus 2NH3 gives O minus SO2 NH minus plus 2 NH4 plus. Thus, it behaves as a dibasic acid. Amphoterism. A compound that dissolves both in acids and bases is said to be amphoteric in character. In aqueous medium, zinc and aluminum hydroxide are amphoteric. In liquid ammonia, zinc amide shows amphoteric behavior. This is illustrated by the following reactions. That is, reaction of zinc hydroxide with HCl, zinc amide with ammonium chloride in presence of liquid ammonia, zinc hydroxide with the sodium hydroxide in aqueous medium, zinc amide with the sodamide in liquid ammonia. Ammonolysis. Ammonolysis in liquid ammonia is similar to hydrolysis in aqueous medium. In hydrolysis, the concentration of H plus or OH minus ions increases due to the interaction of cations or anions of the salt with H plus or OH minus ions furnished by the autoionization of water. Whereas in ammonolysis, the concentration of either NH4 plus or NH2 minus ions increases due to the interaction of cations or anions of the salt with NH4 plus or NH2 minus ions furnished by autoionization of ammonia. These ammonolysis can be explained by the following reactions, that is hydrolysis of copper sulfate and ammonolysis of tin 4 chloride. Complex formation reactions. Complex formation reactions are similar to reactions occurring in aqueous medium. Consider the reaction. Zinc nitrate react with sodium hydroxide in aqueous medium to form zinc hydroxide and sodium nitrate. In this case, zinc hydroxide is insoluble. That zinc hydroxide again react with sodium hydroxide in aqueous medium to form soluble hydroxo complex, that is Na2ZnOH 4 times. Whereas zinc nitrate react with potassium amide in liquid ammonia system to form insoluble zinc amide and potassium nitrate. That zinc amide again react with the potassium amide in liquid ammonia to form soluble amide complex, that is K2ZnNH2 4 times. Similarly, many metal amides, imides and nitrates dissolve in a solution of potassium amide in liquid ammonia, forming soluble amide complexes. That is AgNH2 react with KNH2 in liquid ammonia to form soluble amide complex, that is KAgNH2 twice. Reduction reactions. Alkali metals dissolve in liquid ammonia, giving blue-colored solutions, which are strong reducing agents as they can readily supply electrons for reduction process. Sodium metal in liquid ammonia, for instance, reduces copper iodide to copper. Oxidation reactions. Oxidizing action of various oxidizing agents is weaker in liquid ammonia than in aqueous solutions. KMnO4 in liquid ammonia act as a very weak oxidizing agent. KMnO4 is reduced by a solution of potassium in liquid ammonia to K2MnO4 and finally to MnO. Solubility of substances in liquid ammonia. Liquid ammonia is a pure solvent for ionic substances due to its very low dielectric constant. Amongst the inorganic compounds, nitrates, thiocyanates, perchlorates and most of the cyanates are soluble in liquid ammonia. Whereas oxides, hydroxides, carbonates, phosphates, sulfates and most of the sulfides are insoluble. Ammonium salts such as ammonium nitrate, ammonium thiocyanate, etc. are soluble in liquid ammonia and most of the metal amides except those of alkali metals are insoluble. Solutions of alkali metals in liquid ammonia. The ability to dissolve the alkali metals is one of the striking features of liquid ammonia as a solvent. The alkali metal solutions in liquid ammonia are blue in color. The blue color is characterized by its color, which is independent of the metal involved, its density, which is similar to that of the pure liquid ammonia, its conductivity, which is in the range of conductivities of electrolytes dissolved in liquid ammonia, and its paramagnetism, which indicates the presence of large number of unpaired electrons. The alkali metal solutions dissociate to form alkali metal cations and ammoniated electrodes. The electrolytic conductivity of the blue color dilute solution is due to the dissociation of metal solution into alkali cations and ammoniated electrons. As the concentration of the solution is increased, M plus and E minus species associate, resulting a decrease of conductivity. Very dilute solutions of alkali metals in liquid ammonia are metastable, and when they are catalyzed, they undergo decomposition. ENS3 exclaims minus in presence of Fe2O3 gives NS2 minus plus half S2 plus X minus 1 NS3. As the concentration of metal increases, the blue color changes to bronze, and finally the color disappears altogether. On evaporating the alkali metal ammonia solution, the alkali metal can be recovered. The blue color of dilute metal ammonia solution is attributed to the presence of ammoniated cation as well as ammoniated electron.